Welcome to this video on Year 1 Statistics, Chapter 3, Prep Practice Test on Data Representation. So the first question, the lengths of a group of beans are recorded in centimeters. The quartiles are of length Q1, that's the lower quartile, 12 centimeters, Q3, the upper quartile, 18 centimeters. And then we're given an algorithm here that a bean is longer, than the third quartile plus 1.5 times the interquartile range, or shorter than the first quartile minus 1.5 times the interquartile range, is an outlier. Now, in an exam, you'll generally be given an algorithm. You don't have to memorize this algorithm. It may be the same, it may be different, but whatever algorithm they give you for deciding what is an outlier, you need to apply it. And one of the things you need to do is to work out what the boundaries are of such an algorithm's decision as to whether it's an outlier or not. So whether they ask you for the lower and upper boundaries or not, you should calculate them. So in this case, the lower boundary is Q1 minus 1.5 times the interquartile range. The interquartile range is Q3 minus Q1, 18 minus 12 is 6, 1.5 times 6 is 9. So 12 minus 9 is 3, and 18 plus 9 is 27. So the lower boundary is 3, the upper boundary is 27. And these give us the outliers. And basically what that means is that if you have a distribution represented, for example, like these box plots underneath, then outliers are marked with asterisks, and then the whiskers would then end at either the previous value or the upper boundary or lower boundary given by the calculation here. So for part B, so which of the beans with lengths 3 centimeters, 20 centimeters, 25 centimeters, and 28 centimeters are outliers? Well, if we examine them, excuse me, in turn, we see that the 3 centimeters lies exactly on the boundary, but isn't shorter. Okay, so it needs to be less than 3 centimeters to be an outlier below 3 centimeters. The 20 and the 25 are clearly not outliers. The 28, because it lies above the 27, is an outlier. So the only outlier is the 28. Okay, question 2. The lengths in millimeters of two species, A and B, of insects are summarized by box plots. So a box plot, we represent the lowest value by one end of the whisker, the first quartile by the start of the box, the second quartile, the median, by the middle of the box, and the third quartile, the end of the box, and the upper whisker being the biggest value. If, however, we're using outliers, then any outliers are marked with asterisks, and then the whisker below that is either the previous value or more usually the boundary that we calculated. Okay, so in this case, we're asked to compare the lengths of the two species of insect. Okay, so we've got type A and type B. And we can see from the box plots what the median is. So the median of type A is about 9 millimeters. The median of type B is about 18 to 19 millimeters. So when comparing two distributions or two sets of data, there are really three things that we can do. We can compare a typical value, which is an average. In this case, from the box plot, we can read off the medians. So we can talk about the typical length of type A species and a type B species. The second thing we can do is we can talk about the spread. The spread can be given by the range, the interquartile range, the gap between Q1 and Q3, and there are other measures of spread that we will come across. But you could talk about the spread, that's the second thing. And the third thing you can talk about is the skewness. Skewness is to do with the shape of the distribution, and it can either be symmetrical, which basically means that it's evenly distributed with a peak in the middle and symmetrical either side, or it could be unsymmetrical by being skewed either to the right or to the left. The peak, the tail being to the right is right skewed, the tail being to the left is left skewed. You don't need to worry about skewness for this part of the course, but you can, if you know about it, you can certainly mention it. So comparing the two lengths of the species, we can see that type A and type B have similar spread, looking at Q3 minus Q1, or the range. Their skewness is different. You can see that the type A is right skewed, with the tail being a bit more to the right, looking at the gap between Q3 and Q2 and Q2 and Q1, but you don't need to mention that. So they're approximately similar spread, but typically type B insects are longer than type A insects because we can see that their median length is significantly bigger, about 18 to 19 millimeters compared to about 9 millimeters. State giving reasons whether an insect of length 17 millimeters is likely to be of type A or type B. Well, if we look at 17 millimeters, we can see that it lies within the range of both of them. So it is possible that it's a type A insect or a type B insect. But if we look in a bit more detail, we can see that 17 millimeters is within the middle of this distribution of type B, but it's actually at one far end of type A. So you can say that, or you can make a statement about probabilities, but be careful because we don't know what the probability of it being 17 millimeters is. We can discuss the probability of being more than 17 millimeters or less than 17 millimeters, but we can't really say what the probability of being 17 millimeters is from the information we've been given. So what I've said here is more likely to be of type B because less than 25% of type A insects are as long as 17 millimeters. And more than half of type B insects are this length or longer. So you need to make a statement about greater than or equal to or less than or equal to. You can't really make a statement about being equal to in this case. Question 3. This is a very typical exam question and one that we really need to understand, and a favorite one that students often ask me about to repeat and to go over again. So feel free to do so. So we have a frequency table with class limits and some frequencies. And then we're told the histogram is drawn. The class with the limits 45 to 50 is represented by a bar width 3 centimeters and height 4.5 centimeters. And then we're asked to calculate the width and height of another class. So let me say a little bit about this. When you're drawing a histogram, we generally need to calculate what the class width is, and we represent the class frequency by the area. So if we look at the 45 to 50, the first thing to realize is the boundaries of that bar are not 45 to 50. Those would leave a gap because it's the nearest kilogram. The 45 to 50 actually represents 44.5 to 50.5. So the class interval is that you draw for a bar in the histogram would be 44.5 to 50.5. And note that the class width is 6 centimeters, not 5 centimeters, as you might imagine from 45 to 50. Now, if we use the fact that the class frequency gives the area, that means that the frequency density, the height of the bar, needs to be the class frequency divided by class width. So what's the class frequency for the 45 to 50? It's 9. What's the class width? It's 6. 9 divided by 6 is 1.5. So the frequency density, the height of the bar, you'd expect to be 1.5 centimeters. And you can check that 1.5 times 6 is 9. So the area is representing the frequency. But in reality, you don't actually have to draw a histogram with 6 centimeters and height 1.5 centimeters. As long as these lengths are proportional for all the other bars, it's okay. You can apply a scale factor. And in fact, the scale factor you apply to the widths can be different to the scale factor you apply to the heights. But you have to apply the same scale factor for the width of all the bars in the bar chart, and you have to apply the same scale factor for all the heights of the bars for a bar chart in any one histogram. And this is what we're going to do to answer this question. So I'm going to calculate what the actual scale factors are. So we're told that the width of the bar representing the 45 to 50 kilogram class is 3 centimeters, but we saw earlier that's representing a width of 6 kilograms. Okay, so that means that the scale factor of the class width to the actual width of the bar is 6 going to 3. If you take 3 and divide by 6, the scale factor is a half. Whereas the height, we're told, is 4.5 centimeters, and that represents what we calculated should be a frequency density or height of 1.5. 4.5 divided by 1.5 is 3, so the scale factor applied to the heights is 3. Now we're ready to look at the new class, and the calculated width and height for the 56 to 64 class. 56 to 64 class is what we asked to get. Now, if we look at the 56 to 64 class, the actual boundaries are 55.5 to 64.5, so the actual class width is 9. And then if we take the frequency of 27 divided by 9, we get a frequency density of 3. 3 times 9 is 27. So the frequency density or height that we expect is 3. If we now apply the scale factor of a half to the width, we get 9 times a half is 4.5. And so the width that we'd be representing to be consistent with what was done with the previous bar would be a width of 4.5 centimeters for the 56 to 64 class. And likewise, applying scale factor of 3 to a height of 3, we'd have a height of 9 centimeters. And quickly checking, you can see that actually the areas would be given by a scale factor of 1.5. That's 3 times a half. So for the first one, 3 times a half times 9 is 13.5. 3 times 4.5 is 13.5. So the area of 9 is being represented by an area 1.5 times as big. And here, 4.5 times 9 will be the same as 1.5 times 27. So that's just as a check. But the answers are width 4.5 centimeters and height 9 centimeters. I personally draw a diagram for any of these questions to save me the headache of trying to deal with all that data. Part B, estimate the number of students over 62 kilograms. Okay, so what we're wanting to do here is that we're wanting to calculate how many students approximately are over 62 kilograms based upon the information in this histogram. There are a couple of ways of doing it. I'll take the OR first. You can use this bar or rectangle method that we looked at when we're doing linear interpolation, except that this time, instead of having an unknown value and a known cumulative frequency, we have a known value and an unknown cumulative frequency. But you can fill in the box in the same way. So the interval that we're interested in, if we want to look at over 62 kilograms lies in the 56 to 64 kilogram box with a frequency of 27. So it's actually represented by 55.5 to 64.5 weights. And the weight of 62 kilograms we're interested in, we can locate relative to that at the bottom. And the cumulative frequencies, if we add up 1, 9, and 11, that gives us 21, plus 27, that gives us 48. So there are 21 values up to 55.5 kilograms, and there are 48 values up to 64.5 kilograms. And now what we want to do is we want to find the cumulative frequency that corresponds to 62 kilograms. So if you're using the box method, what you can do is you can say the length x minus 21, x minus 21, divided by the length 48 minus 21, here, must be equal to the length 62 minus 55.5 divided by the length 64.5 minus 55.5. We get this here. And if we make x the subject, we see that x equals 21, which is the lower cumulative frequency, plus 6.5 ninths of 27, which is 40.5. Or the way I would do it, I would say the gap between 62 and 55.5 is 6.5. And so we want 6.5 ninths, because that's the size of this gap, of the cumulative frequency, or sorry, of a frequency of 27 that we need to add on. So 21 cumulative frequency plus 6.5 ninths of a frequency of 27 gives us a cumulative frequency of 40.5 for x. And that means that the number of students up to 62 kilograms is about 40.5, because remember, cumulative frequency is up to. We're asked to estimate the number of students over 62 kilograms. So that means that if there are 60 students in total, 60 minus 40.5, there'll be about 19.5 students with a weight of over 62 kilograms. That's about 20 students. There's an alternative way of doing it, which is instead of working out the proportion to the left, we can work out the proportion to the right. So we could do 64.5 over 62 divided by 64.5 minus 55.5 of the 27 frequency, and add that on to the 12, which is that frequency here, and work out the area to the right. So in other words, work out this proportional area here and add it to the area of this histogram here. Okay, I think probably the second one would be favored by most students, but the first one can also be done. Okay, I hope you find that understandable. Please let me know if you need any further explanation of any one of these.